Hey buddies, are you there? Hey there. Let's see. Can you see the whiteboard? It just says AP Physics C Mechanics. I've got the chat open too.
Yeah.
Okay. I was trying to get my OneNote to sync up. You know how every time my board has an update, it takes me a minute to get them synced back together? Well, same thing's happening here today between my personal computer and my school computer or school account. Anyway, it is what it is. Can you see just the whiteboard, or do you see the chats on the side? I'm just not sure how much you see.
If you click on the chat button, then you can see the chat on the side.
But you don't, you only see my, like you only see what I'm drawing and stuff like this.
Yeah, we just see the white and then the text.
Hi.
Yeah, we can see that.
Okay. Whoa. Somebody got excited about that. Oh, I have to be careful about touching the screen with my pen. That's a hot mess. Okay. Okay. So Harrison noticed that the video that I posted had no audio, and I haven't gone back and dug into my YouTube channel to see if it's just on mute or what, because I'm also trying to get my children to do this kind of stuff, to do their online learning. It's all kinds of fun. So I said to him that I would address any of those questions today, because today is supposed to be a WebAssign work day, right? They're gonna see my hand. So what, I guess what questions, if any, do you have at this point? Any questions?
Can you help me with part 11D on the WebAssign?
Let me get it pulled up. I only have like 2 computers, a laptop, a phone, and my bamboo board. Yeah, whew, okay, let's see. So I need to view number 11, correct?
Yeah, part D of number 11.
Okay, so we've got the 2 boys sliding towards each other on a frictionless ice-covered parking lot. Jacob, with a mass of 45, is gliding to the right. Ethan has a mass of 31. Whoa, I gotta figure out that. That's not what I expected to do just then. Sorry, buddies. Okay. When I change my screen, do you still just see the whiteboard? Is what it's
Yeah,
called?
we don't see you looking at it.
Okay, so you don't see that I'm trying to pull up WebAssign so that I can copy this question in there?
No, we do not see that.
Super, thanks. All right. Oh, people are waiting. Let me get these people in, hold on. Who's iPhone 5? Y'all are so silly. Okay, I'm sorry. I wasn't looking at my participants, and was not paying attention. I was not attending to all the things. Isha, you asked this question, right?
Yeah.
Okay. I'm just trying to get, I was going to put the question on the screen so that if anybody is not actively looking at the question, they can see it. So that's what's taking me so long. I'm getting there. Okay. And I'm trying to navigate this new thing that I'm using. Oh, goodness. Eight, 11.
Mildew.
All right, let's see if this is going to work. All right, so you can see the question with the,
Yeah, we see the question.
thanks. And then Isha, you specifically, so I'm guessing that you figured out what their speed was when they just collide with each other because there's no external force on the system. So their linear momentum is conserved. So I'm assuming that you just did a regular old momentum conservation for part A and part B to find the final velocity. And so in part C, find the velocity of their center of mass. That's also going to be just conservation of momentum because the speed of the center of mass doesn't change. And you can actually just use the conservation of momentum for a sticky collision, and that will be the speed of the center of mass. And then specifically, what is their angular speed after this extra thing has happened where they are not colliding head on. So let me see, put this over here. Okay, it was so much fun. The boys repeat the collision. Can you see that? Maybe. Okay. Again, I'm still trying to get used to this. What is this? Can I zoom out? Can I? Darn it. Hi, Navinka. I'm still trying to figure things out, so bear with me. Can't tell what's happening. Crap. No, she's talking. Oh, I'm trying to monitor the chat on the side. I paused my screen sharing because I'm struggling here. I'm going to try to figure this out because I think that I don't love using the whiteboard option for this. Everybody in here? Oh, Nuno. Hey, Nuno. Nuno just joined. I don't know if y'all can see those things, but he did. Okay. I've paused the screen sharing because I was trying to answer a question. I'm getting used to this. What is happening? I don't know what's going on. I have the strangest little doohickey. All right, so I just moved that around. So that happened. Let's see. Let's see, screen. Hey, friends. Okay. Oh my gosh. Okay, so what you're seeing is my old OneNote folder, and it's making me crazy that I can't see the new OneNote folder. And for right now, I cannot see the chat. So I'm gonna try to get it back over here so I can see it. And such. I don't know. Okay. Why can I not insert a? Oh my gosh, I'm so sorry. He's just like, I'm not going to come to these ever again. All right, so here we go. I'm getting there. I'm getting there. It was so much fun that the boys are going to redo this whole thing, and it's so much fun. Let's see. Let's get some slightly bigger font here so you can see it. And I'm going to tab all over the place because shift. Here we go. All right, so we have the two boys. This is number 11 from the WebAssign, and the two boys were moving towards each other, ice frictionless, so there's no external forces acting on the system. And okay, so we've got their mass and velocities, and they're going to meet and grab on. And so much fun, they're going to do it again, but they're going to be a certain distance apart. So I'm going to go and just check real quick. Nope, I'm not. I'm lying. I'm a big fat liar. Chat. Is anybody saying anything in the chat? I can't tell. No, she's talking. Okay. So no news is good news. All right. So let's see if I can do this. It's been a while since I used my my bamboo board, so it's been kind of fun. All right. So you've got Jacob and Ethan, and Jacob is gliding to the right. Oops, you know what? They are not going to move head on to each other, okay? They're going to be separated by this distance that was given, the 1.4 meters there. So let's see. So Jacob is moving to the right, and this question was 8.19 meters per second. And Ethan is gliding to the left, and he's moving at 10.7 meters per second. And this one has a mass, this is going to be important, of 45 kilograms. And this one has a mass of 31 kilograms. And they are separated by, let's use this fun pencil I have here that's like rainbow or galaxy or something. Anyway, so it's 1.04 meters apart. Okay, so at the closest approach, they lock arms and start rotating about their common center of mass. And we're going to model them as particles and their arms as a cord that do not stretch, and then find the velocity of their center of mass. So the velocity of the center of mass should be the same as it was earlier. Oh my gosh. Cortana, I don't need you. Is that correct?
Yeah, it's the same.
Okay, great. Because the conservation of momentum is still the same. Nothing has changed in terms of conservation of momentum. Now, did you find the center of mass of the system?
Yeah, I had different numbers, and I can't find my work for it right now.
Okay, so I'm just kind of partial to the big dude. I know. I just a lot of times I'll choose. Oh my gosh, I'm trying to get used to this pen again. Sorry, it's acting a little weird. So I'm going to use this as like my y equals 0 or my position 0, and then I don't really care that this is down or up. They were just separated by a distance. And so then that means that Ethan is sliding at a distance of 1.04. And so that makes 45 at 0 and 31 at 1.04. And then we're gonna 45 plus the 31 there. And then I wish I knew what was going on. Oh, that's not even the same color. That's exciting. Where did I even get this color? Oh, excited. Sorry, talking out loud. Control Z is not working. All right. So let's see. Oh my gosh, please stop. Please stop. I hope you're all laughing at me at this ridiculousness. Meeting controls. All right, I don't see anything in the chat. So don't send me anything in the chat you don't want me to show to the group, because it's just gonna be right somewhere. No, she's talking. She's talking, Milland. All right, that's good. All right, so then 31 times 1.04, and then divided by the 45 plus 31. Oh, yeah, I did divide it by not plus. Okay. Unless, well, I most likely don't know what I'm doing, but I got 0.424 meters. So that means that somewhere around here, when they meet, they're going to start spinning. So I'm going to use the conservation of angular momentum, and that initially we have an angular momentum of Jacob, and I'm going to let that one be positive because it's moving to the right. And then I'm going to have Ethan's angular momentum initial be negative because he's moving to the left. And truly my momentum would be to the left, the radius, so the momentum would be to the left. Then you swing your fingers into the radius because here's the radius there. And so if you do the right hand rule, then your thumb is into the page. So put your fingers in the direction of P, put your fingers in the direction of P, and then wrap your fingers so they swing in line with R, and then your thumb will be pointing into the page. So then this would be equal to the final angular momentum of the system. Okay, I can't tell if y'all are commenting, so I guess just chime in if you have a question, because it's hard for me to toggle back and forth. I'll get the hang of it. And then we'll go back to school, right? No. All right, so then this one is Mr. V. because it's a particle. So we got the 45. R is going to be, so this distance here is 0.424. So M, R, V, okay, and then minus 31 times, then I need this distance here because that'll be the R for Ethan. And so that's whatever 104 crud minus 0.424 is. And then its velocity is, his velocity is 10.7. And then, so that is the initial angular momentum of Jacob minus, no, it's not time. Go rest. You got 30 more minutes. Go read a book. Please? No.
Can I read a book to Millie?
Yes, you can read a book to Millie. All right. And so then afterwards, they are a system of two particles. So the moment of inertia, so this, let me grab another color over here. So this final angular momentum will be I times omega. Now the I of this new rotating system of kids will be mass Jacob, R Jacob squared, plus mass Ethan, radius Ethan squared, all times their final angular speed. So that's what's going to go in over here to the far right. So then I'll have the mass of Jacob times 0.424 squared plus the mass of Ethan times whatever that 1.04. I don't have a calculator. Well, I do. It's in my left hand right now, but I'm in the middle of writing and I don't want to mess up. Probably gonna mess up anyway. Anyway, squared, and then, oh my gosh, I almost had enough space. Oh my gosh. Trying to get it to scroll over. Oh, stop. Ah! So professional. The most professional ever. I think we're gonna have to zoom out. Just a wee bit there. And then I'll clean this stuff up. I thought I would. I guess I can't erase with my regular mouse. Oh, goodness gracious. I can do this. Choose rate of stroke. That's good enough. All right, let's get rid of this stuff. All right, so then this is the moment of inertia of the system after the collision, and then this should be the final angular speed. So, stop. So let's see what we get here. I'm slow as crap with this calculator. Sorry, buddies. Oh, I'm going to mess up. Times. Ugh. Okay. I'm going to. Did anybody else get negative 48.062 for the left side of that big nasty? And then
I had different numbers, but it was really close.
yeah, you had different numbers, but like, did I do my math right? Because, you know, I'm
Yeah, that's what
struggling.
I got.
Super. Yay, y'all are out there. It feels a little weird. I'm sitting in my dining room and I'm just talking about physics and I can't see that you're participating. I'm just talking into the ether and doing my calculations on my calculator. All right, and then in this big brackety parentheses looking thing, good grief, I got 19.85 and then times omega. Ooh, so they're gonna spin, they're gonna have a negative angular speed. They're gonna be spinning. Yeah, they're gonna be spinning. Oh no. I did something wrong. Did you see what I did wrong? I got excited about explaining the direction of, oh shoot, of the,
Yeah, WebAssign says it's wrong, but
yeah, girl, because I can't do it. I'm real dumb. Hold on. Stop. Oh gosh. Hold on. Stop. All right. I just need all this crap down here to be closed. Oh, so buddies, I did the right hand rule for Ethan, but I didn't do the right hand rule for Jacob. So the momentum of Jacob is to the right. So put your right hand fingers to the right, and then his radius, you have to swing down below. So you're gonna have, oh my goodness, I'm such a ditz. All right, so for Jacob, you're gonna have his momentum is to the right, but then swing your fingers down, R, and you also get into the page. So this should be a negative, and this should be a negative, and that is gonna be a different number. What do you think about that? You don't sound excited. Oh shoot, maybe I'll be faster now. There's parentheses.
okay, it works if you treat them as the same sign.
My gosh, what is wrong with me? Every time I touch the flipping page, I just mess everything all up. Nope, that is not what we're doing. That is not what we're doing. Where's the page that we're doing? Oh, good Lord. Oh, wait, that looked really familiar. This is not looking familiar. That does not look familiar. That does not. Where did I put that page, friends? Untitled? Untitled. Top stories, apparently. Sorry. Sorry again. Oh gosh. Oh, there we are. There's our thing. There's this thing. I was trying to get everything to open up.
I don't mean to like throw off your rhythm here, but I just wanted to ask about the part we did before the conservation of angular momentum when they were rotating, but did we use just linear momentum to find the velocity of their center of mass?
Yes.
Why can you do that if some of their momentum is like rotating at the same time?
So remember when I kicked the stick in class and it slid across the floor when I kicked it in the middle? And you can see the right page again right now. I didn't.
Yeah.
So when I kicked the stick and I kicked it in the middle, the whole thing just slid. When I kicked it off center, the whole thing slid and it rotated. So some of the, let's see, if I could kick the stick with the same kick every time, the speed of the center of mass of our stick would be the same no matter what, because I'm imparting the same linear motion, linear momentum. Now, because it was off center, you get some rotation that also occurs. So think of it as like when you do this conservation momentum, there's also an energy transfer. And so so you have linear energy and you have rotational energy. And because of the collision, you're also adding rotational energy to the system. So there's nothing to reduce the speed of the center of mass. Just because it's moving in a circle after the collision. Does that, I don't know if that made sense or not.
It does, mostly. I just don't, like, I don't know. I don't get this either.
Let's see.
Do you, so from a conservation momentum standpoint, you don't, like the speed of the center of mass doesn't change, but
Correct.
the energy changes because now some of it's going into rotating while some of it's going into translating?
Yes. So right, so we found the velocity of the center of mass, and we found their angular speed, and then what fraction of their original kinetic energy is still mechanical after they link arms. So what did you find? What's the, so there's 100% of their original kinetic energy is still mechanical energy after they link arms, compared to the sticky collision, right? Didn't they just stick together? They grab onto each other and hang on. So in the case of the collision, when there's just linear momentum, I guess it's like the energy that was transferred out of the system during the collision is now the energy that goes to making them rotate, because it's like there's an outlet for that energy. When they grab a hold of each other, they start swinging each other around rather than smacking and having to slow down and speed up like they were to begin with. And I'm using my hands and like you're sitting in front of me, but no, it's actually just the garbage cans in the cul-de-sac that apparently I'm teaching to today. So I think your question was maybe about this fraction of the original kinetic energy. So like in this example that I pulled up, and I think you can see my screen, only 27%, pardon me, not 20%, oh my gosh, 0.27% of the original kinetic energy is still there after the collision. So it's a highly energetically losing, high loss energy, highly energetically, I don't know, something with lots of energy is removed from the system of the two people during the collision because of the POW. Like they have to it's like a car colliding and they have to smush together. So there's a lot of energy transferred to, maybe breaking their bones or something like that. We're not going to hurt anybody in physics, never mind. But then in the case where they rotate, all the energy that was transferred out of the system because of the collision is now used to cause them to rotate.
That makes more sense. Thank you.
You're welcome. All right, so Isha, I think it was Isha, had the original question. So how are you doing now?
Yeah, it makes sense now. Thank you. I forgot the -2.
Yep, and I had to look at it, and then before I got to the end, I thought I'm dumb because this is one of those cases where they are both, if you think about them spinning around the circle, their initial motion is tangent to the path that they're going to take and in the direction. You know, they're going to spin like clockwise. And if you take Jacob's motion and continue it clockwise, and also Ethan's, and go around like that. So I think they should be like Jennifer and Evie, because women are underrepresented in science. Why it has to be boys having so much fun that they repeat the collision, I don't know. Okay, what else? That was a good one. Thank you, Isha, for jumping in there and asking a question.
I'm having a lot of trouble on the like back half of 8.
Said it's time to go away to Daddy movie. And she says, oh Connor, and she's looking at me. It's time to go away.
Can you hear my kids? Because that's cracking me up a little bit. All right, let's see. He's putting, we have a new puppy and we have no school, so everything's a little bit chaotic. Okay.
It's time.
No, it's not. There's 15 minutes left.
15.
Yes. Go set it. Go wiggle your tooth and see if it'll fall out. Go. It's really loose. All right. So the back half of 8. So can you be a little more specific?
Like
May I-
D. Well, I would say D, E, and F, but I haven't started E and F because I couldn't get the answer to D.
Okay. So what's the angular speed immediately after the collision? So the hinge is fixed. So that means that linear momentum will not be conserved in this collision because there is an external force making thing here. So so there's not just the, God, I hate that alt text. The bullet and the door interact with each other, but the hinge is interacting with the door, so it's like the third wheel. You know, it's like really not, we really don't want you. So in part B, I'm assuming that you found your angular momentum to begin with, and then after the collision, your system is going to be the bullet and this rod. Oh, I don't want to copy the alt text. Let's see if I can get this copied over.
Also, if a question asks about mechanical energy being constant, is that basically just asking if linear momentum is conserved? Because that doesn't have to do with rotating, or that does refer to rotating?
Mechanical energy is any kinetic or gravitational potential energy. I always think of mechanical energy as energy I can see that an object has, like an object is moving. And I can see that it is an object, and I see that it has mass, and I see, or must have mass, it's an object. It's moving, so it's kinetic energy. I can see that this object is above the ground, so it has gravitational energy. So then what wouldn't be mechanical energy? That's like chemical energy, the energy stored, nuclear energy, the energy stored in the atomic arrangement of electrons and protons, or even I guess electromagnetic radiation, light energy, so to speak, sound, the motion of the particles. So mechanical energy is usually gravitational potential energy and kinetic energy. So when the question asks you something, some words, is mechanical energy of the bullet door system constant in this collision, meaning is it conserved? No, it's not, because it's going to stick, right? Is the bullet going to stick? Whoops. Embedded, yes. So it's a perfectly inelastic collision. So then I know that the energy is not going to be, mechanical energy is not going to be conserved. Therefore, it's not going to be constant.
So it doesn't have to do with the hinge. It has to do with the fact that it's inelastic.
Yes. And the only kind of, if a hinge is present, then the collision momentum cannot be, linear momentum cannot be conserved. So yeah, it's about what kind of collision it is more than anything. Okay, so I was trying to make this a little bit bigger so we could see it. Oh, look at that. Okay. Oh my goodness. Okay, so the bullet, all right, so the important thing here is that this is 1 meter, but the bullet is 1 meter minus 11.9 centimeters, so 1 minus 0.119. So the bullet is 0.881 meters from the hinge. And I'm assuming you used that to find your initial angular momentum as being m of the bullet, v of the bullet, times r of the bullet. That's a b. And you use that for this angular momentum. Now, after the collision, it's going to be a system of hinge, bullet, rod rotating together. And so we're going to need the moment of inertia of the rod bullet system. So we can do it as the rod and the bullet and their final angular speed. So now the moment of inertia of the bullet is, hold on. Stop freaking out. I don't even know what's happening. Did somebody take over my computer? Stop. Backspace. Okay. That got all weird. All right, so then your moment of inertia of the rod will be, it's about the end, so it should be 1/3 the mass of the rod times the length of the rod squared, plus the moment of inertia of your bullet should be the mass of your bullet times the rotational r, that same 0.881 for your bullet squared. And so that's your total moment of inertia of the system after the collision. And then you're looking for, what is this angular speed? So does that work out for you?
I think so. I'll have to like put it in my calculator, but
Yeah.
that makes sense.
Okay, so was there a piece of that you were missing?
I think I kept trying to like do something with the fact that it wasn't in the center, so I don't know.
Oops, I accidentally closed something. I don't understand what's going on. So, I wish I did. No. Screen sharing has stopped as the shared window is closed. Well, yeah, of course, because I had a snafu over here.
Okay, it worked. Thank you.
Sure. Sorry, I don't seem to be working right now. Can't figure out. Oh, this might be an issue. I hope someone has hacked me because that would be better than my computer acting like it's having a spasm. All right. I wish you could see this. Well, maybe you do. No, you don't. The screen sharing has stopped because my computer was having a fit. Okay, sorry. I think I'm back. Ashish has entered the room 5 minutes before the end. Oops. What is this? Show grid. What have I done? Someone's hacked me. Oh, we have 6 participants. Everybody's left. Aw, so sad. Yay, Isha has stayed with me. Sanvika has stayed with me. This is exciting. And I guess, Kate, are you iPhone 5?
Yeah.
That's funny. Okay, I didn't know.
That's
So,
just the name it's auto-populated as. That's what my device is named.
okay, so are you looking at it from your phone?
I'm watching it on my phone, and I have website on my laptop.
Oh, cool. That's awesome. I'm just real curious about how all this is, panning out here. Now in the chat, Kevin, are you still here? I thought I saw a question that Kevin said, I know it's super basic, but how do you do 8F? I feel like that's what we just did, or something similar, or maybe not. 8. A, B, C, D, E. Can you still just see the one note, or do you see that I'm all over the place?
We can just see one note.
That's super. Okay, because I'm opening up all kinds of stuff. All right. Okay, so part F is what Kevin had asked about for the same question, the swinging door question. Now imagine the door is hanging vertically. What's the maximum height after the collision? So we're going to use a conservation of energy. Now, energy is not conserved from before the collision to after the collision, but we're using like conservation of momentum conservation of energy from the moment they collide. So let's see if I can get this pasted in here. From the moment they collide to the moment they stop swinging together. Oh my gosh, I'm struggling. How have your other online classes gone? Better than this one? All right. So let's get this plugged back in. Maybe it will behave. Yeah. All right. So in this case, you've got your hinge and your door, and I'm drawing it kind of like so that it doesn't look like before, but it looks like here's the bullet and it has embedded into the door. That is so ugly, but you get it maybe. So that's the bullet.
It makes sense.
And here's the door. Okay, and there's the hinge. And so after the collision, this hinge door bullet system will have an initial angular speed that I think is what you're finding right here. That this final angular speed of the collision is the initial angular speed for the swing. And so using the conservation of energy, the EK, and it'll just be rotational, is converted to EG. Because of this hinge, there's no linear motion, so there's no linear kinetic energy, or translational kinetic energy. So you got to do the 1/2 I omega squared is equal to mgh, and that we're looking for the maximum height there, so that's the piece you're looking for there. And then so then you just have to use that moment of inertia that we found earlier, which was the 1/3 mass of the rod, length of the rod squared, plus the mass of the bullet times the radial distance. Remember, this is still whatever that distance was squared, times omega squared, which is this initial angular speed of the swing is the final angular speed of the collision. And then all together, the oops. All right, I just got a little bit weird there. Please stop. Please stop. I'm trying to go from tablet to mouse, and it just doesn't love it. I need to stop trying to do that. So then, all right, what are we going to do for the, so the MGH? So that will be the height of the center of mass. So let's say that the center of mass is like, there's a bullet, the center of mass of the door is like in the center, so the center of mass of the system might be like right here. So when we do this height, it's going to show me how high, this will be H, that the center of mass translates or moves through. And so the bottom of the door will also, because it's, you know, connected, it'll also swing through the same height difference. No, it will not, will it? It will not. That is not the same height. I'm a liar, liar, pants on fire. Oh, is Kevin still around? Because he asked this question. Kevin? Well, I'm down to 5 people. Oh, Kevin's still here. That's exciting. Are you excited, Kevin? Oh, wait, there's a chat. He says, yeah, I get it now. All right. So, but Kevin, I lied. I lied about H. So don't get excited about how you get it right now, because I'm dumb and I lied. I'm a liar, liar, pants on fire. Okay. Oh, shoot. All right. I'm glad you only see my one. Sorry, that's my kid. So this is L minus L cosine theta. Where that L is the distance from here. Y'all are killing everything in the house. What is up? That is this distance L right there. Ugh, this is an ugly picture. Okay, so if we, hold on. Usually if I draw over here on the side. Okay. Oh, I know why my kids came downstairs like crazy, because I was like, y'all, oops, y'all have to stay upstairs until 2 o'clock. And I guess they've done a pretty good job of staying upstairs until 2 o'clock. So I have to give them some grace there. All right, so I just moved the whole thing because it's ugly. Okay, so here's the rod, okay? And here's the end of the rod, and here is the ground. And the bullet is like right here, so we'll put it right there. And the center of mass of our rod will be at L/2. So this is L/2.
Does the bullet not change where the center of mass would be just because it's so?
No, it does.
Oh.
It does. So that's the center of mass of the rod. This is where the bullet is. Here's our hinge. So that's our bullet. So our new center of mass would need to be, let's see, mass of the rod, center of mass. Oh my gosh, why does it keep doing that? Somebody has hacked me. Okay, so the mass of the rod times L/2, and then plus the mass of the bullet times the distance the bullet is from the hinge. So I'm using this right here as being my 0 position. That's where R is equal to 0. Then I'm going to divide it by the total mass, M rod plus M bullet. Now, that's going to be something. I don't know what it is, but it's going to be something that's probably, oh look, I'll use my little rainbow picture. I'm going to say it's going to be probably like right here. Oh my gosh, stop doing the weird thing. I'm going to have to wind up ordering a new board. Amazon's going to make so much money off of me while I'm stuck in the house. Okay, so that's my new center of mass. So when you use the conservation of energy from before the collision to after the collision, hold on. I gotta figure out how to, shoot. Okay, so when you're finding the H, it's gonna be like that distance, H. And that H, oh gosh, magenta purple H. I can't even control Z. Everything's stupid. Everything is stupid. Escape. That's nice. Escape worked. I'll get this together in a second. All right, so this H will be equal to the L minus L cosine theta, where this is the distance to the center of mass. So I'm going to draw a very exciting looking bracket. We'll call this L. So then the end of the rod is going to go through the same angular displacement. So we need to find theta. So from energy, you can find H. So this is from the energy equation. Not for, but from, because I can't spell.
Mommy, can I watch a movie during this time?
Yeah.
Thank you.
And then L is from the center of mass distance. From hinge to center of mass. So then we can find this. find the angle the rod swings. So TH, the rod swings through. And then once we have that, then we can use, get excited, we can use that L is minus L cosine theta, where it's the same theta here. And this L is the length of the rod. So both of those are the length of the rod, and that'll tell us what finally, what is the height of this end of the rod. So, I keep clicking on things and they do dumb things. All right. Chat. Okay, so Kevin says, I get it now. I messed it up though, so I hope you caught that. But that was a 202. So hope you hung in there with me. All right, my children have lost their minds.
We have not. I'm just putting her back in her bin.
And so I'm going to stop this, and if you need further help, just send me a message. And I will get better at doing this because there's no other option. So anyway, stay home. See you later. Kinda. Bye.